Okay, so I want to write natural log of 1 plus 15x as a power series. And so far, in order to do that, what we know is what? A over 1 minus r. We can write functions kind of this form or related to that form. All right, so we got natural log of 1 plus 15x. How does that relate to a over 1 minus r form? So we looked at this last time. If you were to take the derivative of that, what would it be? 1 over 1 plus 15x, but then by the chain rule times 15. And so then I could rewrite that as 15 over 1 minus negative 15x. And now I've got a over 1 minus r. And we notice what? The antiderivative of that will be the function we want. So we can write this one as a power series and do the antiderivative of that power series, and that will be equal to that one, right? So a over 1 minus r. So we got some more room here. Okay, so I'm going to do 15 over 1 minus negative 15x. And we know that's equal to 15 times negative 15x to the n. And that's for n equals 0. Right? Geometric series. And so what is this? We've got a negative, so in all here we've got negative 1 to the n, right? Negative 1 to the n. We've got how many 15s? So we have negative 1 to the n, and then we have n 15s plus 1 more 15, so that's 15 to the n plus 1. And how many x's? N x's. Okay, so that thing right there is the same as negative 1 to the n, 15 to the n plus 1 more, 15 to the n plus 1, x to the n. All right, and let's write out some terms of that. So I think we get when n equals 0, we get 15. When n equals 1, we get negative 15 squared x. And then plus, when n is 2, 15 cubed x squared, and so on. Did I do the math right? Did I make a mistake? Does that look right? Etc. Okay, on and on and on. Okay, and so because this was exactly the derivative of natural log of 1 plus 15x, the antiderivative, so we're going to do what? Antiderivative is going to be natural log of 1 plus 15x. So I'm going to do antiderivative of this with respect to x, and then do all these terms, and then make sure that those match up. So, like I said before, with a polynomial, we're pretty confident we can get that right? We're pretty confident we can get this right antiderivative, and then we can use that to check what we get on just the summation form. So antiderivative of 15 is 15x. Antiderivative here is minus 15 squared, what? X squared over 2 plus 15 cubed, antiderivative of x squared, x cubed over 3. One more, 15 to the fourth, x to the fourth over 4. All right, so provided we didn't make a mistake there, that needs to be the result of the summation form that we come up with. Okay, so antiderivative will be -1 to the n. So anything that doesn't have an x in it is just going to come along for the ride. It won't change, right? So then I have, what, x to the n plus 1, and that divided by n plus 1. So now, does starting at n equals, so what do we need to start at? What do we need to make our n start at so that we get these terms here? So if n equals 0, do we get that first term 15x? Looks like it, right? We get x to the first divided by 1, 15 to the first, and -1 to 0 is positive 1, so that we want to start at 0. So now remember when we set up the similar function that we could do the geometric thing on, it's not, we had examples where it's not always taking the derivative or taking the antiderivative doesn't always get us exactly the function we want. So sometimes then we have an additional step where we multiply by x, or we divide by x squared, or we multiply by 3 or 2. So remember, we start with a geometric series that we know we can do. And then by taking the derivative or antiderivative, we either get the function we want or something close to it. And if it's something close to it, then we have an additional step, multiplying, dividing, something, to get exactly the function we want. But then when you do it to the function, you have to do it the summation notation, and you have to do it to all the terms as well. Okay, so any questions on these? You got 2 more nights to work on these. So this one maybe kind of had a little bit, this was easier. Sometimes you get a little tricky. You really have to refresh and know your rules of exponents really well to make the simplifications and to do the algebra that you need. So just be really careful. And this is your chance to really nail down your understanding of the exponent rules, because that's a big part of this. Getting these right is all the little details with the exponents. Any questions on this example? Okay, so that one will be due along with the new one on Wednesday morning. So now where we want to go with this is a very, these types of functions that are like a over 1 minus r, that's a very narrow class of functions, right? So in terms of writing functions as power series, this is very limiting, right? You've got a very specific form of a function, like a natural log, or one that looks like very close to that for this technique to work. So can we broaden that a little bit? Can we do better? And that's where Taylor and Maclaurin series come in. So we say that relatively few functions, of all functions, relatively few are of the form a over 1 minus r, or related to that by differentiation. So the technique we've been doing so far is kind of restrictive. It's not, it only allows for, like I said, a very narrow class of functions that we can write as series. So Taylor and Maclaurin series allow for writing any function as an equivalent power series, not just ones that are like a over 1 minus r. So when you have these, like a Taylor series, it has a center point. So it's building the power series about a particular x value, and that's normally x equals a. Okay, and so here's the form of that. Well, let's show why this is true on Wednesday. Okay, well, we're going to just state it today and use it, and we'll show why it's true on Wednesday. And here it is. So this is referring to the nth derivative. This is the nth derivative evaluated at a times x minus a to the nth power over n factorial. Okay, so just make sure you know that that means the nth derivative of f. So what is this about? Well, we're starting with some function. We want to write it as a power series. And what is a power series? Essentially, a power series is what? What's the idea of a power series? So we're doing all this work, but we got to know what it is before we're like getting into all this algebra and pushing symbols around. We better know what a power series is. What is a power series? In essence, generally, what is it? What's that? It's like a polynomial, right? It's like a polynomial, but with an infinite number of terms, right? So there's all kinds of functions that are not polynomials, right? Trig functions, exponential functions, logarithmic functions, and all kinds. Inverse trig functions, right? So can we take any function and write it as a polynomial? That's the idea, okay? And so what this is saying is we can do that by information from the derivatives of the function, right? So if you have the function, so you're starting with some function, say it's a trig function, okay? Start with a trig function. Using information about the derivatives at a particular x value, we can build the Taylor series based on those derivatives. That's what this is saying. Okay, so now a is a constant. All right, if a is a constant, see this, think what? See this, think what? Go. And just a is some constant. X is like 2 or -4. Remember that n is the derivative, the nth derivative, right? Nth derivative. So you use like prime notation, right? Prime notation for the derivatives. Okay, where's Francisco Diaz? How'd you do? Where are you getting the ones? So start again. So maybe I just misheard you. Go ahead. Okay. No. Let's see. So the 0th derivative is just actually the function, evaluating the function. So it's going to be the function evaluated at A, then what else? Zero factorial is 1. So yeah, so the first term is A. How about the second term? What's the second term? It's not to the first, right? What did we say n was here? The nth derivative, right? So when n is 1, we're talking about what? F prime. F prime of, okay? Is that it? What else? No, we're evaluating for n equals 1 now, right? So we got 1 factorial and x minus a to the 1. All right, what's the next term? Where's Monty McRae? Thank you. How about Yifu Pei? Yifu Pei? Here? Yeah. What's the next term? Second derivative? Hmm? Okay. Is that it? Is there more? Is that it? Right, we've got this part too, right? What's this? Over 2 factorial, right? So this is what you should wrote. 0 factorial is 1. 0 factorial is 1 by definition, okay? It's not 0. It's not 0, it's 1. Okay, so it's building a polynomial, right? But then centered about A. And so we'll see later in class, we'll see what that's about. This idea of it being centered at A, how that forms the function as a polynomial centered at A. Okay, but this is the general form. Okay, so now a Maclaurin series is a Taylor series. It's a specific Taylor series when the center A equals 0. Okay, so it's a specific Taylor series when we're centering about 0 or A equals 0. So now I want you to write both the summation form and what it means for a Maclaurin series. It's a Taylor series when A equals 0. So what would the summation form and the expanded form of a Maclaurin series be? Go. Okay, where's Sunomi? Beg me. How'd it go? How about the summation form? Did you do the summation form? Good. F derivative. Okay. So it's not that x is 0, it's that a is 0. So a is 0, not, it looks like you're doing x is 0. All right, anything else you want to change? What? Okay, so if a equals 0, we get this. And then, where's Cameron? Cameron, go watch. Yeah. Did you get the individual terms of this? Is this what you got, first of all, for the summation? Okay. Going from this answer, could you do the terms? Okay, go for it. Okay, but a equals 0. Maclaurin series is when a equals 0. Yeah, so it's going to be the 0th derivative, evaluated at 0. Then what? First derivative over 1 factorial times x to the first. Good, one more. Uh-huh. Good, all right, got it. So this is the specific Taylor series centered about a equals 0, which is called the Maclaurin series. And so these are easier because with a 0 you don't have the x minus a or x minus whatever, and all your derivatives are valued at 0, which usually makes life nice. Okay, so this is usually the easiest version of a particular Taylor series because things drop out. 0 is friendly to work with. Okay, so let's write the Maclaurin series for y equals e to the x. So what do we need? So what we need is, the key to writing these Taylor and Maclaurin series then is we need these derivatives evaluated at whatever our center point is. If it's a Maclaurin series, it's going to be center 0. So it's really helpful to make a chart to get those factors, right? What we're after is all the derivatives, or the first several derivatives, evaluated at 0. Okay, so we'll write in here, n equals 0, 1, 2, 3. And then once we have those, then we just assemble it, right? The rest is just writing down the right factorial and x to the n. That's easy. That's the easy part. So it's basically coming up with these is the key to writing it, and then the rest you just write down, right? There's nothing to think about. The rest you just write down. Okay, so the 0th derivative of a function is the function. Okay, so the 0th, so this is f, when n equals 0, you're talking about f of x, right, e to the x. Okay, so now we want to evaluate that at 0. What do we get? Evaluate the function at x equals 0, 1. Okay, so now this is now the first derivative. What's the first derivative of e to the x? E to the x. And we want to evaluate that at 0. 1 again. Second derivative of e to the x. All right, so we see the pattern. All the derivatives are e to the x. And so then evaluated at 0, it's all 1s. So for the e to the x, all of these derivatives evaluated at 0 are 1. Do you follow this? Does it make sense? Okay, write down the Maclaurin series for e to the x then. What's the Maclaurin series for e to the x? Where's Muhammad? Al Abdullah. You get it? Anything else? E to the x equals, like this? Is there any more? Something else. Is that, so that's not a series, right? That's not a series until we have, yeah, we still gotta have the sum, right? The sum of, yes, you got the formula right, but you gotta have that too. All right, so what is that? 1 plus, when x is 1, you get x. When n is 2, you get x squared over 2 factorial, x cubed over 3 factorial, etc. Okay, now the question is, again, we've seen this before, what's the interval of convergence? So is this for a particular interval that this works, or for all real numbers, or what? So how are we going to find that out? Do the ratio test. This is a nice easy one. So the ratio test is, so for the interval of convergence, we're going to do limit as n goes to infinity, x to the n plus 1 over n plus 1 factorial times n factorial over x to the n, which leaves us with x to the n plus 1 over x to the n. Where's Alejandra? Cantu. What's x to the n plus 1 over x to the n? Just asking what x to the n plus 1 over x to the n is. X. Right, x. We've got one more x in our product of x's. We've got one more in the top than we do the bottom. All right? How about n factorial over n plus 1 factorial? Where's Vincent? Bagnara. Where's Vincent? Here today? Vincent? Not here? Where's Jasmine? In Zuza. Yeah. What's n factorial over n plus 1 factorial? 1 over n factorial. All right? Adrian, Victor. Where's Adrian? What do you think? Is that, she got that 1 over n factorial? 1 over n plus 1? Yeah, that's right. Yeah, so remember, n plus 1 factorial is the same as n plus 1 times n factorial, right? N times n minus 1, etc. So then those go. What's the limit as n goes to infinity of this? For what values of x? Is it 0? All values of x. So for what values of x is this limit less than 1? Doesn't matter what x is. You always get a limit less than 1 or 0. So what does that tell us about this power series for e to the x? Yeah, so for all values of x, this power series will converge to e to the x. So let's see that in action. Here we go. Let's look. Any questions on setting up the power series for e to the x? Anybody have a question? So let's see that here. Okay, e to the x is the red graph. And what is this? What am I showing here? We've seen this before. It's the... So now I have capital N set to 0. So what I'm showing here is what? And I've got k's instead of n's. 0 to 1. So what am I showing? I'm just showing the first partial sum. I've got capital N set at 0, which means I'm not showing the whole Maclaurin series, I'm just showing this. K equals 0 to 0 of that x to the k. And what is that? It's just the first term, right? Just the first term of the series, or 1. And so when you graph that, what? You get what? So is this a good representation of e to the x? What's right about it? What's correct about it? There is one thing that's correct about this representation of e to the x. Right. So you get the right function value at x equals 0, right? 1. That's the only thing that's correct about it. Okay? So now if I do the second partial sum, and I go k equals 0 to 1, I'm going to get, what will that partial sum be? 1 plus x. And what will that look like? So that will look like this. So here's the second partial sum. Maybe. There it is. What's correct about this? We still got the function value, but then there's something else correct about this. What else is correct? What's that? Okay, and so that's referring to what? Oh, it's not only more closely aligned, but at 0, what about the rate of change? Exactly right. So look, so now we got, when you do the second partial sum, and this was what? This had to do with what? F, just the function value, and that's what we got. We got the function value. And now this one has to do with what? The first derivative evaluated at 0. And look, the first derivative evaluated at 0 is correct. You get the function value and the first derivative. Okay? What's the next partial sum? 1 plus x plus? Is that too many? Yeah. So this is 1 plus x plus what? X squared over 2 factorial. So notice what's happening. Since we're centering at 0, it's where the power series is a good representation is around 0, right? So it's going to be around 0 where it's going to be a good representation. And now we have the function value, the first and the second derivative correct at 0. But now also we've got a good approximation, say from about negative 0.75 to 0.75. Because those first two derivatives are correct, now we have kind of an interval where we're actually approximating the function pretty well. So with every term that you add, as you continue to make the partial sum longer, you get one more derivative correct at x equals 0, and you've got a wider range of values around 0 that are doing a good job approximating e to the x. So the longer of a partial sum that you take, zoom out here. E to the x gets big fast. Let's see. So the more terms that you take, the better, the more of an interval around 0 it's going to be close to the original function. Okay? So here with the 21st partial sum, it's pretty good all the way out to like -8. And around 0, very, very, very good. We can't see the difference anymore. Okay? So if you were to add together all infinitely many terms of that series, you would get the function e to the x. If you were able to add every single term of the polynomial, you would get e to the x perfectly. Okay? The more terms that you add, the better and better it gets, starting from 0 and working its way out from 0. Okay, let's try a different example. Oh no, let's build on this one here. So we saw the series converges for all real numbers. It approximates the entire function, or it's exactly the whole function if you were able to add all infinitely many terms. And so now we can use that. So, for instance, e to the 4th. How can we estimate e to the 4th using our series that we built? What would e to the 4th equal according to the power series? How could I use the power series to estimate e to the 4th? Where's Cambria Baston? Is Cambria here? Not here. Ricardo Ornelas. Ricardo Ornelas? So how can I use this? So we built this power series for e to the x. How can I use it to estimate e to the 4th? What would I do? Yeah, tell me. So tell me. Okay, so what would it be? But I want to use the series, so I want to use, I don't want this, right? I want to use what this means to estimate it. So how can I estimate e to the 4th with what we did? So it's all about, again, it goes back to see this, think what, right? See this, think what? And then how can we use that to estimate e to the 4th? Yeah. So tell me. 1. So I want e to the 4th now, e to the 4th. Where's Yaslin? Costa. What do you think? Okay, so tell me. So you want to go from n equals 0 to 4? Is that what you're saying? So does n equal 4? When we're saying e to the 4th, is that n equals 4? What equals 4? Trevor, what do you think? Okay. So what equals e to the 4th? What equals e to the 4th according to this? Yeah, so right, so in order for it to be e to the 4th, we'd need all infinitely many terms, right? We need all infinitely many terms to get e to the 4th. But because the sequence is what? The sequence has to go to 0, right? The sequence is going to 0, that's for sure. Then every partial sum gives a better and better approximation of e to the 4th. So let's see that. Same thing. Same file, in fact. So what is e to the 4th? E to the 4th is 54.59815,003. Okay, so let's look at, so the power series is, I've defined the power series as f of x, okay? It's our power series. But that's for partial sums of capital N. So we'll do f of 4. So when we just have the first partial sum, it's just 1. Second partial sum is going to be what? 5. 1 plus x. 1 plus x squared over 2 factorial is 13. So we keep adding terms, 23.6, 34, 42, 48, 51. Here's the 10th partial sum, 54.154. So what's happening is we're converging in on e to the 4th with every additional term that we add. Do calculators have the value of e to the 4th just as in their database? Do calculators have e to the 4th in their database? If they did, how big would the database have to be for that? Right, so there'd be an infinite number of values like that we could ask it to calculate. Sine of 3.6, cosine of -100, right? So it's not a database. What does a calculator do? It does a power series. It does a power series with just enough terms of the partial. So here I am at the 22nd. Once I get to the 22nd partial sum, is it exact? It's not exact, but it's precise to that many decimal places. How many decimal places is that? 3, 6, 8? Is that 8 decimal places? All right, so once you get to the 23rd partial sum, it's correct to 8 decimal places. And so if that's what the calculator is showing, then any more precision, it doesn't matter. Okay? So no, it's not exact, but it's close enough to 8 decimal places. And that's what calculators do to calculate these decimal approximations. They use power series. Okay? They use series with enough precision so that the error is small enough so that we get it correct to however many decimal places the calculator shows. Okay, so this stuff is incredibly useful. No, we're not done. What are you doing? Sorry if I'm boring you. Okay, so that's one thing you can use these for. One thing you can use these for is like estimating e to the 4th, okay? So what about now, instead of starting from scratch, we can use the e to the x to say, build the power series for e to the -3x. What would it be? So now, so it's like the new input instead of x is -3x. So it would be what? -3x to the n. It's just like how you think of a function, right? Over n factorial and then whatever that is. So just by building the power series for e to the x, we know almost instantly really e to any function of x by substituting that function in for x. Okay, and you all can handle that. All right, what about this? X squared times e to the x. So here's another variation on e to the x times x squared. What would that be? So now I want x squared e to the x. Well, it's just going to be x squared times the power series of e to the x. So I'd have x to the, I heard someone say n plus 2, right? I'm going to multiply by x squared, just like we did in the other ones. So it'd be x squared times x to the n, which is just x to the n plus 2. So now this is the power series for x squared e to the x. Notice that the first two terms of e to the x were 1. What was this again? 1 plus x plus, it's up here, squared over 2 factorial, etc. So what would this be? So this is something to think about. E to the x minus 1 minus x would be what power series? So here's the power series for e to the x. So what about e to the x minus 1 minus x? What would the power series for that be? If that's e to the x, what would this minus 1 minus x be? Do you notice here's 1 and here's x? So what would this whole thing, e to the x, minus 1 minus x be? We would just start here. So that would be the power series, what I boxed in red, e to the x minus 1, right? Minus 1 minus x. Would be then, what would be left would be starting at n equals 2. It'd be the same series, but starting at n equals 2.